So I will start by thanking all the members of the jury for having accepted to review my PhD projects. And I will present my works on the predicting the propagation of acoustic waves in complex media with deep neural networks. So the context of this thesis is about the aerodynamic generating noise, which is found in several industrial applications, such as aeronautical, wind turbines, heat, ventilation, and air conditioning, or the next generation of drones and urban air mobility. What they all have in common is that noise regulations are becoming stricter, and therefore there is a need to predict more accurately and faster their acoustic generated noise. So now going into the details of the modern propulsion architectures, what they all have in common is they have increasing complex acoustic propagation effects. As you can see here, there is three typical examples: the counter-rotating open rotor on the left, the ultra-high bypass ratio on the right, and on the bottom part, the jet pump, which is basically a device that helps driving the air, for example, in the air conditioning systems of aircraft. And as I said, they all have in common that the acoustic generated waves are affected by both the installation effects and the complex mean flows. So that's it. And therefore, in order to improve the acoustic signatures of all these devices, we need to have fast and accurate predicting tools that will be used in the pre-design phases of these devices in order to improve such acoustic signature. So now I'm going to review some of the classical approaches used in acoustics in order to predict this sound propagation. First of all, and the most rapid one and the most computationally fast one, are the analytical models. These find closed form solutions of some equations, and they are indeed very fast. The problem is that they use some strong modeling hypotheses. For example, when we want to calculate the response of some blade or some cascade of blades, we typically do the hypothesis that there are flat plates. And what we typically use is some calculation of Green's function, or the Amiet model, or the Binet-Hoff method, etc. Then the next step is the hybrid computational tools. These are pretty fast for being computationally, and they are also very modular. So that means that we can separate the calculation of the acoustic sources using, for example, some CFD method or analytical sources, and then the subsequent propagation into the far field, so into the observer, is done through an acoustic analogy. The main drawbacks is that there is no acoustic feedback mechanism taken into account, and also it's pretty hard to take into account very complex installation effects. So in order to take all this complexity into account, we have to go to the so-called direct approaches, where now we are going to resolve at the same time both the source, the acoustic source, and their subsequent propagation into the observer. And this is done through high fidelity numerical codes. Of course, the main drawback is that because these codes need to have a low dissipation and low dispersion properties, we need to use high order schemes, and therefore this has a very high computational cost. And ideally, what we would like for these pre-design phases I told you before is some fast methods, but that take into account as much complex effects as possible. So basically the mean flow effects and the geometrical installation effects, typically, for example, found in direct applications. And how can we improve these kind of methods? So in this work, we decided to go into the field of the data-driven surrogates, and in particular of deep neural networks, which may help us find these new and these novel acoustic propagation tools. So what is a deep neural network? It's just an arbitrary function or operator approximator, which we will call throughout this presentation as G. And it's defined as such. So this G takes as input some vector of inputs X, and then it's going to predict some output Y hat, shown here. In order to train, so to parameterize this neural network through these parameters theta shown here, we need to compare this output with a target, Y. So this is coming from a database. By comparing these two quantities, we will define a measure of the error, which is called here the loss function. And this will help, through an optimization problem, find the optimal parameters, so this theta star, that parameterize as best as possible this whole pipeline. Now, this is some very typical approach found in many other applications, but when we try to apply this to physics applications, so in particular for our acoustics, there is typically some challenges found. The first one is that there is a low availability of databases found in our acoustics or fluids. Also, that the existing databases are typically limited by the training physical parameters, so it means they are limited in Reynolds number, in angle of attack, in Mach number, etc. Also, that when we use a purely driven method, probably we will have some inconsistency in the physics. And finally, that there is, for the moment, few guarantees on these surrogate solvers on the accuracy or the stability of the methods. And this is contrary to classical PDE solvers, where we have many years of investigation on these subjects. So the idea is then to, in order to tackle these challenges, to go towards what we call the knowledge-guided machine learning. So that's basically means to combine large quantities of data of these databases with our prior scientific knowledge in order to solve these challenges. So this is going to be the approach we're going to follow in the rest of the thesis. Now going into the detail on how to define our acoustic neural network surrogate, so this deep learning approach, what we need is to create a four-bar propagation model predicting some acoustic quantities, so this y hat, that's gonna take into account the mean flow and geometric installation effects. In order to do that, we need some existing science-based models, so some existing, for example, PDE solver. And in our case, we are gonna use some direct computational acoustic solver. In particular, we are gonna use a compressible Navier-Stokes solver called IVVP, and also a lattice Boltzmann solver, which is also compressible, called Palabos. This is gonna be used for generating our databases. And then, in order to validate these simulations, we are gonna again use the same type of numerical solvers and also some analytical solutions. Finally, the goal of all this is to replace this existing science-based model, so F, with a deep learning-based method. And the question now is to determine which type of neural network we have to use. So in order to do that, we are going to review quickly the types of the typical approaches found in neural network literature. So the basic one is the so-called fully connected neural network, called also MLP, for multi-layer perceptron. And what it does is just taking some inputs shown in blue here, the X vector, which it will find some output Y in red. And the function is parameterized by some weights and biases, W and B, and it's post-multiplied by an activation function, which is a nonlinear function. Then we can stack several of these so-called layers together in order to increase the representational capacity, so the approximation capacity of this surrogate model. The problem of using this kind of neural networks is that the inputs or the outputs are agnostic to any topology in the initial data, because we have to use vector columns. So therefore, we need a lot of examples in order to approximate accurately a given function, and more in the examples we will find later, which have a very high dimensional, they are very high dimensional problems. So these are very data intensive methods. Furthermore, because we are using these dense matrices W, this is also a very memory intensive method. The solution to this is to go towards the inductive biases. So it means to bake in some a priori knowledge on our neural networks in order to improve the design of such architectures. So in order to do this, we first focus on the spatial inductive bias, and in particular, the convolutional neural networks. So these neural networks are doing the hypothesis that two points close in space are more correlated than two distant points. And therefore, the solution is to limit ourselves to convolve the input, for example, a Cartesian image, with a local and learnable filter, so shown here in orange. And this is live throughout our input. This will then result in a so-called feature as shown here in red. So basically what this is doing is just learning a stencil on a Cartesian grid, and the properties of this neural network is that they are equivariant to spatial translation. And because they are sharing this learned filter throughout all input, they are much less computationally expensive than the previous case. The problem, as you can see here, is that the output has a smaller dimension as the input, so the red has a smaller dimension than the blue, and therefore, and this is because we are not imposing any boundary conditions here, and the question is how to impose them. And this is done throughout what we call the padding. So we need to have the input feature size equal to the output feature size, and we need to add these gray pixels, these gray cells, in order to keep those two sizes together. And the question then is how to choose the values that we add into these padded values. And this will be one of the problems we have studied in this thesis. About examples we can find on this approach in fluid or wave mechanics applications, we have identified two important ones. The first one by Turi et al., where they replace a rand solver with a convolutional neural network, as shown here in the image, and it's basically a multi-scale neural network. Furthermore, Ajuria y Aramendi et al. Also use the same type of multi-scale neural network in order to replace a Poisson equation solver. And the idea to get from this is that these kind of CNNs are able to learn the spatial gradients of the problem, and also because of the multi-scale CNN architectures, they can focus on multi-scale physical problems. Also, another important thing is that the boundary conditions can be explicitly given by using this IBC vector, as shown here in the image, which gives the spatial position of some given boundary conditions. Now going into the problem of temporal inductive biases. There are several approaches found in the literature for fluid and wave applications. The first one, which we call the direct application, and is, for example, found by Ricey et al., is just to use a neural network G to map directly the spatiotemporal coordinates, xt, to the solution of a PD, for example, U. The second approach is to map instead the state of the PD solution at some point xt into the state at the next time step, so t plus delta t. And this is the approach we're going to follow throughout this thesis, since it allows use by just training once this neural network, this G, it allows changing, for example, the initial or the boundary conditions, whereas the first approach forces us to retrain at each new set of initial or boundary conditions. So this is what I say here. Then focusing on the second type, so the operator type of temporal approaches, there is again two families of these. The first one is the one where they first try to reduce the spatial dimensions in order, so the dimensions of the spatial problem, and then this reduced latent vector will be advanced in time through some neural network. So this is, for example, the reduction, for example, is done through some reduced order modeling, for example, Ph.D, so proper orthogonal decomposition, also autoencoder neural network, etc. And then the temporal problem will be dealt with some recurrent neural network, for example, which will focus on long sequence of these latent vectors. And this is typically found in a wave application by Soderberg et al., where they train a surrogate model using this approach on this type of cylindrical waves, and then they will test it. They test the generalization capacity of this approach on a plane wave initial conditions, as you can see here. The problem they show is that for late times, so here, at prediction, for example, 59, the wavefronts of this solution are not well predicted, since it was trained on only cylindrical waves. Therefore, the neural network is just learning by heart the training database. So we see that this type of approaches are hard to generalize outside the training range where it was trained on. Another option then is to keep the convolutional approach for the whole time, and therefore there is not going to be any spatial order reduction. And this will help us focus on the important thing, which is actually the spatial gradients. And for the temporal treatment, we will use only short temporal sequences. And therefore, we are actually just approaching the temporal derivatives which do not require long sequences. And this is found in the literature in many examples, for example, Li and Yu, Geneva and Savaras, or Pfaff et al. And basically, it's just, as I showed you before, we are just taking the initial condition, predicting the next time step, and using this next time step as the input of the next prediction, and so on and so forth. So again, this is focusing on the spatial features, and the temporal operator is just done, for example, with a shift operator, which is just shifting the initial conditions. Finally, about this literature review, we need also to enforce, we can also enforce some additional constraints on the loss function. So that's the way we train our neural networks. And some examples are, for example, the minimization of the spatial gradients errors found, for example, in Bandnagar or Li and Yu. And also we can find examples where they directly minimize the partial differential equation residuals in the loss function of our neural network. So the important idea here is that we can add some extra information on the loss function in order to guide the machine learning algorithm to fulfill some physical constraints. So finally, let's sum up our methodology. So we are going to build an acoustic propagation surrogate that's going to use a time domain formulation using a shift operator, as I showed you before, using a fully convolutional neural network in a multi-scale fashion, and this we will detail it later. We will mainly also focus on the choice of loss function and on the treatments of these boundary conditions, which is a very important topic in our acoustic problems. And now going into what are the research problematics we find in this work. The first one is to know how well these deep learning surrogates perform on our acoustic propagation benchmarks. And for this, we have set 3 types of benchmarks. The first one is a very simple and academic one, where we we study the 2-dimensional propagation of acoustic pulses in closed domains. And you can see that the source is an impulsive source and there is no mean flow considered. The second case is again using some impulsive sources, so these Gaussian pulses, but now we change the boundary conditions to open boundary conditions, so non-reflecting ones, and we set some interior obstacles in order to have some scattering of the waves. And finally, we have generalized this method to consider mean flow effects, and we have imposed some shear on the mean velocity, and again considering open boundary conditions, so non-reflecting ones. Because of a lack of time in this presentation, I will just focus on the 2 first benchmarks. Then a second research problematic is more focused on the methodology of the approach, and this is how can we characterize this approach in the context of our acoustic problem. And this, therefore, we have defined some questions, which is what is the error in time and space of the method? What is its capacity to extrapolate outside the training range? Whether it follows physics principles such as conservation equations or boundary conditions, and what is the computational cost. Furthermore, in the Ph.D. manuscript, we have focused on the quantity of data needed to train those methods and their reproducibility. But these 2 last topics, we'll keep it maybe for the questions. So now going into the results, let's start by focusing on the first case of 2-dimensional propagation in closed domains without mean flow. The problem here is to first assess whether this methodology works at all, whether it can generalize outside its training range, and whether it's consistent with the known physics of the problem. For that, we have generated a database using, as I say, a direct computational approach, where we are going to solve this wave equation on the fluctuating density. We are not going to impose any right-hand side of the wave equation, and therefore the acoustic source is considered through these through these initial conditions, so this Y0. Finally, the boundary conditions are set as von Neumann boundary conditions, so these are reflecting types. Finally, for the initial boundary conditions, we set a random number of acoustic Gaussian pulses in the domain. The interest of having this simple case is that the waves stay trapped in the domain for a very long time, so it allows us to evaluate the long-term error behavior of this approach. Then for the numerical setup, we use this compressible lattice Boltzmann solver called Palabos, and using this recursive and regularized BGK collision model, which is more stable than the traditional BGK model for inviscid flows, actually. And for the boundary condition, we employ the traditional bounce back algorithm. Then as parameters, we are going to use some square boxes with no viscosity. We set the number of iterations of all simulation to a constant. And we define these Gaussian pulses as a random number of them, so going from 1 to 5, in a random initial position and with a fixed amplitude and fixed resolution. Also, we will evaluate the results in terms of this non-dimensional time tau. And what is important to know here is that because we are using the LBM and we are fixing the spatial size of the grid, we are also imposing with this the time step of the method, since the LBM has a constant current number, so this CFL number, which links the speed of sound on the lattice, so this 1/√3, to the physical speed of sound. Then the objective is to learn a time invariant discrete operator, as shown here, where the input will be a series of fluctuating density snapshots at different time steps. So it's k plus 1 inputs separated by a fixed time step, which we call delta t nn, and we will see here that it can be different than the lattice Boltzmann time step. For the outputs, we just want to predict the next time step of the fluctuating pressure field. Once we are going to train this G, we are going to be able to unroll the predictions. So use this in an autoregressive fashion, and this is just using the input at some time step as the output at some time step as the next input, and this is done r+1 times. And so the key parameters here is how to choose the G, the multi-scale neural network, what's the number of inputs, so this K, and what's the choice of time step. Here we have chosen K equal to 3, and the delta time step, the delta TNN, is chosen as 3 times the lattice Boltzmann time step. Here we show what's the type of CNN we are using, which is called the multi-scale one, which was already used in the literature in 2016 for reproduction of video frames, but it was later used for the prediction of wave flows behind the cylinders. And what is important to notice here is that it's just processing the inputs in a multi-scale fashion, using some downsampling and upsampling pairs, followed by convolutional operations. Then, with respect to the boundary conditions, we are going to use using some Neumann boundary conditions, and this is equivalent to using replication padding. So that means we are adding some additional Gauss cells, here shown in gray, and then similarly to finite differences in a center scheme, we are going to impose the values at these extra pixels. Then, with respect to the loss function used to train the neural network, we are using 2 strategies. The first one, where we employ a classical loss, so just the mean square error loss. And then a second strategy where we are also constrain the error on the spatial gradient. So that's what we call the GDL, the gradient difference loss. And here we show the first results. In the first row, we show the lattice Boltzmann case. So we set just the initial condition as a single Gaussian pulse in the center of the domain. And then both approaches, the T1 and the T2, in this autoregressive fashion. We see that, in the last row, we have a slice at the mid-span of the domain. We say that we have a very good agreement between our 2 approaches, the T1 and T2, compared to the lattice Boltzmann. But if you see in the slices, we have at later times some drift in the mean values. And this is actually something that is not respecting the physics of the problem, since the acoustic energy is not conserved. And we actually know that this acoustic energy must be conserved in this type of problem. And why is this? Because if we set the equation for the acoustic energy evolution. We have three terms: the energy density, the fluxes, and the dissipation. Since we are in a closed box, there is no intensity fluxes, and since we are in an inviscid configuration, there is no dissipation. Therefore, this energy density must be constant in time. And therefore, we see that the previous results were not correct. So what we try is to develop a so-called energy-preserving correction to enforce this constant energy over time. And how we done this? So we define this uniform correction epsilon, which we can apply either both at time t on the left equation or at the initial time step, so on the right equation. And after some algebra, we can find an analytical expression for this correction epsilon, which then can be applied after each neural network prediction, as you can see here. So then we are going to show the results as T1C and T2C. That means we are correcting each one of these methods. And so here I show the effects of this energy-preserving correction on both cases by showing again the same slides with the same case of cylindrical pulses. And you can see that there is no longer any drift in the mean values after some iterations. And on the right hand side of the slide, I show the evolution of root mean square error over time for the different approaches. And you can see that for both cases, the T1 and T2, with the correction, we have a gain of one order of magnitude in the error. Then let's study the generalization capacities of this neural network approach. So we are going to study some initial conditions that were not present in the initial training database. And in this case, is the opposite amplitude Gaussian pulses. So we said, as you can see on the left, two Gaussian pulses of opposite amplitude. And when we evaluate the T1C and T2C cases, and we see that we have a very good agreement in both cases. Then, revisiting the same case as Soderberg et al., we again set the initial condition as a plane wave, and we observed that in our case, we are able to predict the propagation with a very good agreement. Furthermore, you can see, and it's visible here, that in the case of T2C, the wavefronts are better predicted. They are sharper than in the case of T1C. And this is because we have constrained the spatial gradients in this second case. So we see that adding these additional constraints further improves our model. Finally, going into the influence of the time step, we have now changed the ratio of time step, so the delta t neural network versus the initial time step of the database, so the LBM. And for each case, we have to retrain our whole neural network. And we see here both the evolution of error versus the number of recurrences, so the number of iterations, and also versus the physical times, this top. And we see that the ideal ratio we found, so the minimum error evolution is with this ratio equal to 8. And this is actually very interesting because we are actually using a CFL condition, so a current number greater than 1. And this is something we cannot use in traditional or classical PD solvers. Also, what we see that why is this value found? There is two factors playing here. So the first one is the compounding of error. So the more iterations we do, the more error we will do. But also, like if we take a very big time step, so in the case of, for example, 64, we see that the neural network is not able at all to predict even one iteration. So we see that there is a balance between these, but we are not sure yet exactly why this value is found. But it's very interesting still because it opens the way for the acceleration of explicit solvers. So now, having looked at this first case, let's go into the treatment of boundary conditions, which is a very important topic in our acoustic problems. So we want to see here whether we are able to generalize the previous application to new boundary conditions, in particular to non-reflective acoustic boundary conditions, and whether the previously used methodology of padding only is optimal or not. For that, we have devised three different methodologies. The first one we call implicit is the same one as before, so we only use the padding to enforce the boundary conditions. The second case is the spatial context one, where we are added an additional input, this IEC, in order to locate the positions of the boundary conditions, so next to the border in this case. And then a third methodology we call explicit. And here we are just masking the border values at the output, and we are enforcing, as you can see, the actual values with some, for example, finite difference equation on the boundary condition. And then we are combining those two in order to provide the final answer. Also, you have to remind that in all these cases, we still need to use padding since we are using convolutional neural networks, and we need to keep, as I told you before, the sizes of the features the same, so we need to use some padding. So therefore, we are also, in each of these cases, we have studied what's the influence of this padding, and in this case, like the serial padding, circular, which is the same as periodic, replicate, or reflection padding. Now going into the what type of data set we are using, we are employing 3 databases, the same type of reflecting boundary conditions, the periodic boundary conditions, and the non-reflecting boundary conditions, which we have generated in the lattice-Boltzmann case, employing absorbing sponge layers. Going into the first case of reflecting boundary conditions, we show the evolution of error for 25 different initial conditions average over time. And we see, we compare the implicit, context, and explicit strategies with the different paddings. We see that the minimal error is found for the 2 cases of replicate and reflection padding, regardless, more or less, of the type of strategy. So we can conclude that for simple cases as the Neumann boundary conditions, it is sufficient to keep the previously used implicit strategy. We can conclude the same if we go to the periodic boundary condition strategy, since we see that the implicit case gives the same type of error evolution versus the context case. But we need to use actually the circular padding, so the periodic padding, because if not, the error will just diverge. And therefore, it tells us that we need some prior knowledge about the problem, of course, in order to impose the padding. Finally, going to the more interesting case of non-reflecting boundary conditions, we again compare these 3 strategies with the 4 different paddings, and we see that in the first 2 strategies, the implicit and the context, in some cases, the errors will just diverge. Whereas in the case of the explicit strategy, for all the different paddings, we have the same error evolution and there is no divergence. So we see that with just the padding is not sufficient now in this case. So when the complexity of the problem increases, we need to explicitly enforce the boundary conditions. And the question now to see is whether we could eventually find some better padding, but this is left for future work. Finally, going to the last part of the presentation, let's now focus on the application of all this previous knowledge to the scattering of waves in complex geometries. So now the questions to answer is whether we can apply the same time strategies to the modeling of interior boundary conditions, and whether we can, with this, model the scattering of waves in these obstacles. And finally, so we are going to evaluate the overall cost of the model. For this, we have again generated a new database using the same type of approach as before, so the same wave equation, the same type of initial condition, but here what we changed is the boundary conditions set as non-reflecting boundary conditions, and in this case is sponge layers. Furthermore, for the interior obstacles, we set as reflective boundary conditions, so the same Neumann conditions as before. We again train this wave operator with this fixed time step, etc. But what is different is that we set an additional input, this IBC, which will set the position of the boundary conditions, so the interior boundary conditions to 1, and the rest of the field to 0. Then again, we are unrolling the trained neural network, and here we are gonna parameterize this a little bit differently as before. In particular, the G, the neural network, will be chosen as a unit CNN, which we'll detail later. The number of inputs here is equal to 1, and the time step found is the same as before, the 3 times the time step of the lattice-Boltzmann database. So the unit CNN follows a similar philosophy as the multiscale CNN we used in the first chapter, but here we are also employing the so-called skip connections, which we see that improve the results versus the multi-scale approach as before. And this was, for example, demonstrated by Cheng et al. And as you can see here, this is where we add on the left, so the so-called obstacle grid, that's the additional information on the boundary condition positions given to the neural network. So again, for the numerical setup, we use the same type of solver, Palabos, and the same type of initial conditions, the Gaussian pulses. And here, the different thing is the non-reflecting boundary conditions. And also, we set some random obstacles in the databases. So we set some cylinders, which can vary from 0 to 3, or some rectangles, we can, again, vary from 0 to 3. And we also change the shape of each obstacle. Then, evaluating the results for this case, the first test case is a very similar one to the training database. So it's just a cylinder located in the middle of the domain, and we set a Gaussian pulse to the right of it. We show, again, the lattice-Boltzmann reference on the top row, the unit prediction on the second row, and the normalized error. So it's normalized by the maximum at each time step. So that's why it goes to 1. And you can see how the error is distributed in space for different time predictions. So we see that we are in a very good agreement with respect to the reference with the LBM, and the main error concentration is seen next to the boundary conditions. And this is actually coming from some spurious reflection or some minor spurious reflection at these boundary conditions. But again, we have a very good agreement overall. Then a second case, which is for the first time testing the generalization in this case, we use some airfoil. So this is a NACA airfoil where we set the acoustic source on top of it. And this is actually it was not present in the training database. And we see again, comparing both solutions, that we have a very good agreement. But interestingly, the error is now concentrated very strongly on the trailing edge, so on this sharp edge. And we see that then there is a kind of error wave propagating in time in having a dipolar shape. So the idea would be eventually to then correct this with, for example, some kind of Kuta condition which will impose the zero jump in pressure, for example, at this trailing edge. But this is something left for future work. A second type of generalization test is the case of the nacelle, where we are using the same type of NACA airfoil, but putting them in parallel, and then setting the acoustic source in the middle of both airfoils. So this is just modeling a kind of nacelle. And you see that we have the same type of error accumulation next to the trailing edge of both airfoils, which is then propagating in a dipolar fashion in both sides. But again, we have a very good agreement, and we see that in this case it's even harder than the case before because we have some dot-like modes appearing inside the nacelle, which are correctly predicted by the neural network. Finally, let's study the computational cost of this methodology. So here I show this table where we have some baselines. So the first baseline is the serial LBM baseline. So we are just using one processor for calculating the response. And then the second one is called the MPI baseline 2, the MPI LBM baseline, which is using 24 processors. And then we are comparing with the different unit configurations, which employ different type of hyperparameters. In this prior to last column, we see the acceleration factor with respect to baseline 1, so how much it accelerates versus this baseline. And we see that from the second case, we have some large factors of acceleration. But it's even the case for against the MPI baseline, so the second baseline on the last column, where we have even a 140 times more acceleration than in the LBM case. And how have we achieved this acceleration? So there is three main strategies. The first one is the temporal portioning. So that means we are increasing the time step used by the neural network versus the time step of the lattice-Boltzmann method. And you can see here we can go up to 3, for example. We have used some parallelism. So this B is just the batch size of the initial condition. So we set some parallel initial conditions, and we set this in one time to the neural network. And then we have also used some hardware acceleration. So we are using some GPUs. So most interestingly, the temporal constraining allows us to really like remove some of the constraints found in traditional PD solvers. So now let's go into the conclusions and perspective of this work. Let's first recap some of the main findings of this PhD thesis. The first one is that we have shown here some of the first application of these convolutional neural network autoregressive methods to acoustic propagation problems. We have built some databases of varying complexities, which have been validated with analytical and numerical simulations. In particular, the first one is the simple closed case configuration in a two-dimensional box, which we have also generalized to the scattering of obstacles in a free field conditions. And we have started extending this method towards considering mean flow effects. And the main results of these works is that it's very important to constrain the physics of the problem. So for example, we have developed the first a posteriori correction, so this EPC, in order to constrain the physics of the acoustic energy over time. And the advantage of this is that there is no need of retraining the whole pipeline because we are doing this in a posteriori fashion. So we can adapt it to the different cases. And we have also found that it's very important to handle correctly the boundary conditions. So this is, for example, what we denominated as the explicit strategy. And furthermore, we have shown that with respect to the computational cost of these methods, they are very interesting since they allow us to relax some of the traditional constraints found in PD solvers. So for example, the CFL condition. Now going to the perspectives of the methodology, the first main question we may all have is what is the future of the method? Will this be used in the future as an industrial, for example, predicting tool? So we have shown that it has a very high potential since it's able to accelerate these solvers with taking into account less constraint as, for example, analytical solutions. But there are for the moment not enough guarantees provided by these solutions. So for example, we see that there are some error accumulation over time, and it's still not clear why we are able to do this kind of coarsening in time, also space. And so therefore we need more maybe mathematical guarantees on these conditions in order to really be able to use this in an industrial fashion. And also it would be interesting to maybe go into a broader perspective and then look into other types of methods. So instead of going into the time domain, going into the frequency domain. And this is, for example, a very recent paper by Stanciola et al., where they have replaced traditional Helmholtz frequency solver using GMRES with a neural network, for example, and they show that the error that they found was lower with a lower number of iterations, as you can see on the right hand side of the figure. So this could be also an interesting venue to investigate in the future. And with regards to the applications, so to more complex applications, it will be first interesting to go towards more complex flows. So this is something we start seeing in the PhD manuscript. So for example, going to non-homogeneous mean flows such as shear layers, but this is only taking into account the mean flow effects. It would be also interesting to go into further complex flows such as turbulent flows. Also, with regard to the type of developing this kind of boundary conditions for being used in neural networks, it would be interesting to go further studying the non-reflective boundary conditions. So for example, to kind of implement the NSCBC, so the characteristic boundary conditions for neural networks, or also taking into account for example, some impedance boundary conditions for modeling liners. And then it will be also interesting to go towards more realistic 3D configurations, since this is what it's required for designing actual aircraft or propulsion systems. So thank you very much. I would like to acknowledge all the people that have, all the organizations that have contributed to this work. And now I will gladly answer your question. And thank you very much for your attention.